Mm, so, hello student. So recall that we are discussing about recall that we are discussing about Markov chain. Okay, and in this discussion we define these transition probabilities by Pij. What is that? This is probability that xn plus 1 goes to state j given that xn is in the state I. Okay, for any n, for any n. Okay, and then ij are actually element of the state space S. So this was definition of transition probabilities. Probability of going from state I to state j. Okay, and then we define transition probability matrices. We remember that we define transition probability matrix, say A, and then that was what? So this was the matrix whose I then J, the entry are nothing but Pij. Okay, and then with the help of transition probability matrix, what are the condition? Condition was summation Pij j equal to say 1 to m equal to 1, where m is nothing but the number of states in the state space. Okay, so so I'm assuming that this is finite. Obviously number of states are finite. Okay, and then the natural question one can ask here, that okay, so do you, if given the transition probability matrix A and this Pij, can you compute this kind of probability, like say what is probability x n plus 2 equal to j given that xn equal to I? So this is a natural question to ask, right? So what does that mean? That means I'm asking that suppose I am in the ith, this is my ith state, and I want to move to the j state. What is the probability that I will go to I to j with two steps, n to n plus 2? What does that mean? That means from I to I will go somewhere, maybe say 1 or something, and then go to j, or maybe I can go to 2 and go to j, and so on, dot 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 dot, and maybe I can go to m and go to j, right? So I was in this xn is taking value I, xn plus 2 is taking value 2 j, and in between xn plus 1 can take value this, right? So what is this probability? So naturally by diagram you can understand that this probability is nothing but sum of all this probability, like you go to here plus go to here, and then finally this, right? So this is, you can easily find out that x yeah, then okay, so let me write down this probability. So probability, then this probability that xn plus 2 equal to j given that xn equal to I. So this is what? This is nothing but probability that xn plus 2 equal to j given that xn plus 1 equal to something, say 1, into probability that xn plus 1 equal to 1, and then x given that xn equal to I, right? Plus, so you can go to one state, you can go to second state also. So second thing can be what? So this is given that xn plus 1 equal to 2, and probability that xn plus 1 equal to 2 given xn equal to I, and plus dot 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 last. What is the last possibilities? It is xn plus 2 equal to j, given that xn plus 1 equal to m, and xn plus 1 equal to m, xn equal to I, right? So you can easily understand that this you can write down as summation, say k equal to 1 to m, right? Probability that xn plus 2 equal to j, xn plus 1 equal to k, into probability that xn plus 1 equal to k, given that xn equal to I, right? This is nothing but the sum, and then by transition probability you can write down that this is the first term. It is nothing but p. So you are going from k to j, so this is p kj, and this is ik. So you can write down this summation over k equal to 1 p ik into p kj, right? So, and then it is clear that this is what. So suppose this is your something, say uh, qij. So that means what is qij? So thus qij is nothing, is the ijth entry of the matrix A square. You know that A equal to the transition matrix. So if you take x square, then A square will be of this form, qij, where ij is nothing but summation probability eik, right? So so this is the general idea, and then one can further generalize this idea, and then this is called n step transition probabilities. Okay. So here you are asking. So let me write down. So let me define Rij of n by this quantity, that you are going from I state to j state in n steps. So maybe xn equal to, say, j, given that x0 equal to I, right? So so from you start with some state, and you are taking n many steps to go j, right? This I am defining my this symbol. So in particular, so in particular, you see that Rij of 1 equal to Pij. Similarly, Rij of 2 equal to Qij. What I just proved so far. Okay. So what do you learn? What do you learn from our last example? One can ask this simple question: Can we derive the general formula for Rij? Okay, and the answer is yes. And this is called Chapman-Kolmogorov equation. Okay, so let me write down. So Chapman-Kolmogorov equation. Okay, Chapman-Kolmogorov tells you that this Rij at n is nothing but sum over Rij of n minus 1. Okay, sorry, Rik of n minus 1 into Rkj of, and then pkj, so single pkj, and your k is running from 1 to n. Okay, for this is true for any n greater than 1. So n equal to 1, you already know that it is Pij, right? And for all ij belongs to the state space. Okay, and obviously this is simple. So how to prove this kind of statement? So again, you just start with a picture. So you are in the state I, okay, and you need to go to state j, okay, in many steps, right? So what does that mean? That means whatever you have, because this is a Markov process, you don't care what happened earlier, you only care what is happening. So this is your xn, it's x0. So you only care what is happening at last xn minus 1, right? So this xn minus 1 can be 1 or 2 or dot dot m, right? So whatever you have before, it doesn't matter, you can go to 1 or 2 or 3 or m, but at the last moment you have to, last step you are taking from either 1 to j or 2 to j or 3 to j, like that. Okay, clear? So these probabilities are simple transition probabilities, and these are your this n minus, so this position is nothing but n minus 1 step transition probabilities, transition probabilities. Okay, and hence by the previous argument, whatever we discussed, we can write down here same thing, that this probability, so this is what, so this Rij of n, which is nothing but probability that you are going from I to j state in many steps. Okay, and this quantity is nothing but sum over say k equal to 1 to m p. So xn minus 1, you reach at kth position from ith position, and then in the last step you are going from x, so the last step you are going to xn, by xn you are going to j step, given what, given that x n minus 1 equal to k and x0 equal to I. But you know that in the Markov property tells you that whatever it is there inside, it only depends on this property. Okay, this is the definition of it is in the Markov property, right? So what does that mean? That means this sum over becomes sum of k equal to this probability that x n minus 1 equal to k, given that x not equal to I, and so this is, there is a probability of symbol here. Okay, probability that x n equal to j and then x n minus 1 equal to k, right? It does not depend on earlier things. Okay, so the first quantity is the transition probability from I to k, and this is transition probability from k to j. So you can so this is k to j, but this is the n step transition probability. This is first one is n minus 1 step. This is one step, right? So this become k equal to 1 to n. Yes, so says you can think this kind of induction or whatever. So this become r ij of n minus 1, sorry, ik rik of n minus 1, and then p kj. Okay, so this is the proof, this is the proof, and this is called Chapman-Kolmogorov equation, and this is going to help us in maybe in future classes. Okay, then we will see that how is going to help to calculate the long-term steady state other things, right? That we will learn later. Okay, so now let us learn something very much interesting ideas. So this is so whatever we are doing for finite many states, and we can do something called classification. How this state look like. So let me write down classification of states. Okay. So so far we have uh, we learned transient probabilities, and but now we are going to define some of the nice definition. So and then we will classify how the states look like, what are the states. So we start with these definitions. Okay, so definition. Okay, so um, so so we say a state J is accessible from a state I. Okay, so I am saying that J is accessible from I. That means you can go from I to J. I if for some n, so n is some natural number. Okay, so n it can be greater than or equal to 1. Okay, and the n step probability or transition probability, n step transition probability, which is defined by Rij of n, is positive. If this is positive, then we call that J is accessible from I. So what is the meaning? So that is, so this means that there is a positive probability, there is a positive probability of reaching J from the state I. So you can reach the state J from the I after some n number of, so n can be anything. Okay, so n number of steps or time, whatever. Okay, clear. So mathematically what does that mean? So you can so equivalently what you can write, so equivalently you can define equivalently equivalently, what is the meaning? That currently, so there is a sequence, there is a sequence of states like this. So we start from I and then go to I1 and then I2 and then I n minus 1 and then j, right? So for some n, so we have in many steps in between and then you go to j. Uh, so these are states. So these start with that starts at I and ends at j. Okay, with what j such that this such that the transitions. So you have the transition from I to I1, then I1 to I2 dot dot In minus 1 to j. These are all positive probability. All have positive probability. Okay. So this is the meaning of accessible. So we start with something I and then you go to somewhere, say something 1 and then go to something 2 or something and then you go to j, whatever you can go by here or you can go direct. Okay, then we call this accessible. So it can be in one state or two step or any and many step. Okay, now we define another definition. So let I belongs to S, so one state. So we define AI. So what is AI? So AI is the collection of all j such that R I j of n greater than 0 for some n. Okay, some n. Okay, so what does that mean? That means AI is collection of all the states which can be accessible from I. Okay, so mathematically what you write? So this is nothing but the collection of all the states. This is a collection of all the states that are accessible from I. Okay, so this is my definition, and then we will define with this help of this we define. So we say that some states I is a recurrent recurrent state or recurrent if for every j that is accessible from I, accessible from I is also accessible from j. Okay, so what is the mathematical meaning? So mathematically, so equivalently, so mathematically it means I is a recurrent if I belongs to AJ, so that means I is accessible from J. I is no, if recurrent, okay, so mathematically I is recurrent if I belongs to AJ for all J belongs to AI. So what does that mean? So that means if J belongs to AI, whatever J which is belongs to AI, so accessible from A, I is also accessible from J. Okay, this is a mathematical meaning. Okay, then we call this type of state is a recurrent. Okay, so I will give an example. Okay, so let me define some more things. Okay, so what does that mean? So the meaning of reference. So when you start a recurrent state, you can only visit the state say J, which is accessible from I, right? So you start a recurrent, you can go only J because you are from J you are coming to I again and you are going to J, right? So that means what? That means if I is a recurrent state, so note. Uh, okay, so if so, what is the meaning that if a recurrent state is uh, is visited once, if recurrence is visited once, it will be revisited. How many times? An infinite number of times. An infinite number of times. Okay, so this is one of the properties of recurrent state. Okay, now we will define another type of states. So another definition, and this is called the transient state. So a state is called the transient state. Transient state if it is not an recurrent. Okay, so what does that mean? That means um, so the recurrent means what? That means if you go to somewhere and you can come back to there. But transient means what? Transient means if you go from transient to another state, you may not come back to transient state. Okay, so in particular, so what does that mean? That means, okay, so let me give you a picture, then it will be more clear. Suppose we have states 1, 2, 3, and 4, and then 2, 2, 1, 2, 2, 3, and then 2 come back here, 1, 2, 1, okay, so 3 and 4, and then say 4, 2, 4. Now you see that I is a recurrent state. Okay, why I is a recurrent state? So this is your recurrent. Why I is a recurrent state? Because see, from sorry, 1 is a recurrent state. Why? Because from 1 you can only go to 1 itself. Okay, and by definition, if you go to somewhere, from there you can come to 1. So I is a recurrent state. And you see similarly 3 and 4 both are recurrent state, right? Because from 3 you can go to 4, 4 to either 4 or 3. So anyway, you will come back same place, okay? But this 2 is a transient state. Note that 2 is a transient state. Why 2 is a transient state? Because from from 2 you can go to say 3, but you cannot come back from 3 to 2. So 2 is a transient state, okay? And I say a 1 and 3, 4 are recurrent state, okay? So in this example, so in the above example, 1, 3, 4 are recurrent, 2 is transient. Clear? So what does that mean? That means once you are you are in transient state, you can be coming to transient state only finite many times, not infinite times. Because once if you go to the recurrent state, and then done, then you cannot come back, right? Okay, so now we will define something called a recurrent class. So what is that? So uh, recurrent class. So now let I be a recurrent state. Then this AI is called the all those j such that Eij n greater than 0, okay, uh, for some j for some n greater than equal to 1, okay. This is called the recurrent class of I. So this is called the recurrent class of I, okay, or simply sometimes class of I, okay. Now note that um, uh, no state outside AI is accessible from AI. So if you start with AI, so you cannot go something outside, right? And so this is one. This is say one, and then number two properties. Um, so I uh, if say J is in AI, the recurrent class of I, so then AI and AJs are same. That means that is uh, recurrent class of any states J of AI is same as AI. Okay. So if you take any element from AI, AI is a recurrent class, then the recurrent class of J is itself AI, right? Okay. So what is the upshot of this thing? Given so remark, or you can say the final portion. So you have a Markov chain. So let M be a Markov chain, and then if you have S in the state space, okay, then S you can write down as union of T is the transient space, union recurrent classes, say some R1 union uh, R2 dot dot finally many recurrent classes, because I started with that S is finite, so we'll have this finally many transient finally Markov chain. Okay, and this is called the decomposition. Okay, so this is called the decomposition of states, so, or classification, whatever. Okay. Mm. So S can write down S in terms of union of. So S is the collection of all states. So this is called decomposition of S of the Markov chain, whatever. Okay, S is nothing but the all the state space of the Markov chain name, right? Okay, so given a Markov chain, finite state Markov chain, you can write down is in terms of this, in terms of recurrent classes and some transient class. Okay, so this now this is homework. You find out that this T may be empty also. T may be empty also, but there must be some recurrent state that must exist. Okay, that you can see. Okay. Clear? So so far so good. So I hope you understood so far what we are discussing. Now we will define another very nice property or idea. So this is called periodicity. Okay. Periodicity. So what is periodicity? So you see that in recurrent class, inside the recurrent class, you may have some recurrent class which has a nice property, and some recurrent class is not was a nice property. So what are these properties? So let me just write down. So we say uh, so a recurrent class, so definition, a recurrent class is called a periodic, it's called a periodic class, a periodic recurrent class if it states, so whatever it states, that state can be further decomposed or grouped, whatever, can be partition in, say, d may d greater than 1, at least 2. So partition in, okay, so maybe I can write down here into d can equal to 1 many subclasses or subsets, and this is we can write down as something, say, S1, S2, and SD, okay, with some property such that all transition from one subset lead to the next subset. So you understood? So You start with one subset and then transition will be next and next and next. So 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 mathematically, what you can say is mathematically it that means that what that okay, so first of all, so you can write down recurrent class R into S1 union S2 union dot SD, okay, D greater than 1, and for um, K equal to 1 to D minus 1, whatever. If you are inside SK, if I is still inside SK and Pij is positive, so what does that mean? That means there is a positive probability that you can go from I to J, then this J must be, this implies J is inside SK plus 1, okay, J is inside SK plus 1, and if K is the final one and if I belongs to SD, see this this is for K equal to 1 to D minus 1, and for K equal to D, and the probability of Ij is positive, this implies that J will be inside S1. Okay, so this is the meaning of periodicity. So you are going from round one side to another side. So let me give an example. So for example, suppose you have 1, 2, 3, 4, 5, and then you have like this, and can go by this. Okay, so 2 to 3. Okay, 3 to 4, 4 to 5, 5 to 4. Okay. Now you see that this 1 is a recurrent state, and it is the also the whole class of 1 itself. So A1 is nothing but 1. Okay, recurrent class of 1. Now recurrent class of 4 and recurrent class of 5 are same, and they are nothing but 4, 5. Okay, and 2 and 3 are transient. You see that 2 and 3 are transient state. Okay, so 2 and 3 are transient. Okay, so and 1, 4, 5 are recurrent. Inside 1, 4, 5 you have the group 1 is one class, say R1, and 4, 5 is another class, R2, right? But even further, R2 you can write down as union of 4 and 5. Why? This is my S1 and S2. You see that whenever you start from 4, you will reach 5. And whenever you start from 5, you reach 4. Okay. So that's why it has a decomposition of two subclasses, right? So this is an example of periodic recurrent class. Okay. Now same example I can make it aperiodic also. How I can make aperiodic? So now let me just add one more, same thing. Let me add one more. So 2, 3, 4, 5. Now let me add one more drawback, that from 4 to 4 there is a probability, right? then it is, see, this is again a recurrent class R2, this is R1, this is T1, this is T is nothing but union of 2 and 3. Okay. But you see that here R2, you cannot write down R2 is a union of, you cannot write down is a union of 4, 5 with the above property. Why you cannot write down? Because if you start from 4, you may not go to 5, you may go to 4 itself also. Okay, so that is violating the condition, and this kind of here R2 is called aperiodic. Recurrent class. Okay, so aperiodic means which is not a periodic class, right? Okay, so what does that mean? That means recurrent class, you can further have two different type of properties. Either you can subdivide recurrent class into more than one number of division, and you can have nice properties, or you may not do. So this is are called aperiodic class. Now we can have this the equivalent property, how to find out something is periodic or not. So uh, equivalent condition of periodicity or aperiodicity, okay, whatever, both. Okay, now you see that so I can let me write down the statement. So let R be a periodic recurrent class. Okay, suppose R is a periodic class, then for any n, and for any n means n many steps that time n, and for any state j belongs to R, there exists I belongs to R such that this transition probability from I to j is 0. Okay, so what does that mean? That means if you have a periodic class, then whatever n you choose and whatever j you choose, okay, you must have a I such that you cannot go from I to n, I to j in many steps. Okay, whatever n you choose. So you start with n and then you can go to this, right? So so you need a proof. So how to prove this kind of statement? So proof. So the proof start with this. Suppose you ask R is a recurrent periodic class, so you can write down S1 union S2 union SD, so union of these because it's periodic things, and let see J and let J belongs to something, say Okay, so you start with so okay, so J is inside R means what? So so J belongs to some Sj, right? One of this, right? Now you can so what does that mean? That means so I'm interested to know, does there exist I so does there exist I belongs to R such that this Rij of n equal to 0. Okay, so this is the question, right? Now you see that the moment you know J is inside some Sj, and these are fixed, S1, S2, S3 fixed, so you can come to J you can come to Sj in many steps from only one step, right? Because it is periodic property, right? So what does that mean? That means um, that 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 so periodicity implies Sj can be reached at time say n from from only one subset. Okay, from only one subset. Something say is um, J dash from only one subset, right? Because see n is given. I mean, the moment you are choosing n, then you find out one I which is outside this, right? So thus if I is not inside that is J dash, then probability Ij of n equal to 0, right? So what does that mean? That means if the periodic recurrent class has a nice classification, you can always you can whatever you choose, okay, and whatever j, so you can always find out one state I, where from where if you start, you cannot reach j state in many steps. Okay, so then what is the meaning of aperiodicity? So thus for an periodic recurrent class, what happened? So if you have a aperiodic class, then there exist, you must have some n naught which is already fixed and a state something say is not, such that for all I belongs to that recurrent class R, that transition probability that P um, from I to is not with n many times, n not many times is always positive, right? The opposite to 1. So you must have n and is not, such that you can always come to you can come to s naught from I in many times for all I, for every I. Okay. For example, in this aperiodic, you see in this example aperiodic things. Okay, so you start with say 4, so 4 is your uh, in this example. Okay, so let me write down this example again. You say you have 4 and 5, and then these and these, and you have these, right? So here you see that your state is not is 4, okay, and uh, uh, your in node is 2, okay. Now if you start with 4, then you can come to 4 by 2, you can come to 4 by this and this, or you can come with this and this, okay. If you start with 5, you can go from here this and this, so you can go after 2 many steps, you can reach always 4, okay, for any I. So I can be 4 or 5, but after 2 steps you will be you will be in 4, okay, clear. So this is the property of periodicity, which is there in is not there for periodic recurrent classes, okay. By this I will stop here the discussion on periodic, aperiodic, and the classification of states. So what do you know? So we can classify or decompose that R. Sorry, decompose my A state space into um, subsets of recurrent states and transient states. And for the recurrent state, you can have further classes, recurrent classes. And inside recurrent classes, you have something called periodic recurrent class and aperiodic recurrent class. Okay. So this is the today's discussion. Okay. Thank you.